Okay, so here are two examples of how to answer application problems from a table of data. Now we've worked with tables of data before when we used Desmos to fit a curve through these, but there are actually some other things that you should look for first before you resort to using Desmos to just identify if there is in fact an easier way to do this. And in terms of an assignment question, on your assignment you know you will be explicitly told to use Desmos, or if you're allowed to use Desmos, it will be explicitly stated. So if you don't see that in a question, then it means there should be something here in the data that allows you to recognize what key properties the function has, and then to go ahead and find an actual equation for that. So in this case, we've got a table of values, and it's representing the height of an arrow over time. We're asked to predict when the arrow will hit the ground. And we've done a similar example to this before. And so if we look at the point of the question, the part where it asks us to find something, here we can highlight that, predict when the arrow will hit the ground. We've actually been through something like this before. So what this is actually asking us to find, first of all, when refers to a time. And so just to be clear, we've got two variables, time and height. So in this case, we know we're finding a time. But as for when the arrow will hit the ground, we know that this also implies something else. Hit the ground implies that the height is equal to 0. So if we're looking for the time when the height is equal to 0, this is what we've been through before. We know that this implies that we need to find the zeros. Okay, if we make a quick model of this, we can see that the time goes from 0 all the way up to 2.5. And that the actual y values for the height, they go from near 0 up to about 20.5 and then back down again. So I know that this is going to be, in general, and this is not an exact model, but we're going to have points here that follow this sort of pattern, okay, where we have this thing at its peak right here at, or rather not necessarily at its peak, but it looks like the highest value from the table is at 2.0, and then we go back down again. So for this reason, what we know is this parabola, we're going to have a quadratic model. It's going to open downward. Okay, it's going to look something like this because we know that it's going to start going down again. So finding the time when the height is equal to 0 means we can find the zeros. We know this thing is going to open downward just from the data in the table. Now the question is, we're not allowed to use Desmos, so how are we supposed to reason about what the actual zeros are? Okay, now you might look at this and say, well, one of them is going to be pretty close to 0 right here. But based on my quick little sketch, the other one is going to be past 2.5, but I don't know exactly how far past 2.5. There is something we can use, however, in this table to allow us to figure that out. So what you should try to look for in the table is, first of all, are the zeros stated? So are the zeros themselves listed in the table? Because if that were the case, of course, we would be done. And it turns out that we don't have any data points when the height is equal to 0. We've got one that's close, but we certainly don't have two. So they're not listed in the table. The next question then is, well, can we identify the vertex from the table? And maybe if we can identify the vertex from the table, we might be able to create an equation and then just use our processes to convert that equation into factored form to find the zeros, or maybe use the quadratic formula. So can we create an equation from the table? And in this case, without Desmos is the key because we're not allowed. And how would we possibly do that? Okay, so I'm going to go through step 1. Actually, maybe I'll just leave that like this. So the question here is, what would we possibly look for to be able to do this? And the only other key points, we only have 3 forms of an equation. Standard form is not one that we can create a model for because the y-intercept itself is not enough information to give us the full equation. So really, if we don't have the zeros from the table, the only other thing we can ask ourselves is, do we have the vertex? Because if we do, we can create vertex form. Now, if we look at the table, we might think, okay, well then I'll just try to look for the largest height. Perhaps that automatically tells me what the vertex is. And so you might notice that if we look at the heights here, we go up to 20.5, and then of course we go back down. So this right here is, in fact, it looks like the highest point from our table. But just to be clear, we can't be absolutely sure that this is the vertex. And why I mean that is, imagine if we had this parabola right here. I'll draw this in blue. Okay, let's say we had a parabola that looked like this. Make sure I do a little bit of a better job. There we go. Let's say we had a quadratic function that had this shape to it. Okay, it is possible for us to have a vertex that goes, in general, above the highest point that we see in our table. So we could have had a situation like this, whereby, if we ignore this point for a moment, we could have had a situation where we were given a couple of points in the table, the y values of the height, they increased, right? They kept on increasing, and then we got to what seemed to be a highest point, and then it decreased from there. But notice that this actually doesn't give us our vertex. So the value that might be in our table doesn't necessarily automatically mean that it's the highest value for our quadratic function. Okay, it could be the case that there's another higher one sitting up here that we just don't have in the table. So how do we verify if that's actually the case or not? Well, we've got this thing that looks like it might be representing the highest point. The key information here, the key thing that we need to recognize is, if this is the vertex, it's going to be in the center of the data. In other words, it's going to have symmetry on both sides. And that is where we might recognize something else in the table gives us that information. So I'm going to highlight this in blue. Notice what we have right here is we have 2 points where the y value is the same. So in this case, the same y value, and we do have 2 points in this case. We have the point 1.5, so after 1.5 seconds, this thing is 19.3 meters in the air. And after 2.5 seconds, this thing is also 19.3 meters in the air. And what this means then is that because these are at the same height, the vertex sits in between these two times. Okay, and so this is true no matter what the height values would be. So long as they're the same, what it really means is that these 2 points right here, these are what allow us to make that conclusion. So we've got this y-axis, if I just make this a little bit larger here, okay, this is our height. And right here at 19.3, I know that these two are at the same height. And what that means then is that my parabola, I know, needs to be symmetric about these 2 points. I know that this is absolutely true then, because if these are at the same height, I know my vertex is going to be halfway between them. So I know that I can do an axis of symmetry here that goes through this point right here. I could continue my parabola in both directions. But this does tell me that the axis of symmetry occurs between these two. Okay, so that's true of any quadratic function. If you take 2 points that have the same height, the vertex will always be in the middle of them. Or if you look at a vertex and you move in equal distance away from that vertex to the left and to the right, so in this case, even if I went further away, if I moved, for instance, 1 second in this direction and 1 second in this direction, I would notice that these 2 points are the same height. So that's true of a parabola because of its symmetry. And so knowing this, then this tells me that the x coordinate of the vertex of the vertex, or what we know as the axis of symmetry, its location, is halfway between these points. And halfway between those points, then, we can calculate that quite easily. So that's halfway between the 1.5 and the 2.5. Okay, so 1.5 plus 2.5, halfway between those. It's easy to see this visually, but we can get the same thing here. That's 2 seconds. And we know that from the graph. So that actually tells us that this right here is our vertex. Okay, so we couldn't just immediately jump to saying that because this was the largest value in our table, that it's the vertex. But now we can say, okay, well, we've found that it has 2 points equidistant from that vertex, or from that, at the same height. And so we now have a starting point. Right? We wanted to be able to say, if the zeros aren't directly in the table, well, how do we find them? We need to create an equation in vertex form. So we can start doing that because at least we know that the vertex form equation is going to be something like, and I'll use the units here in the question, instead of y equals, we'll say h of t is equal to, now there's some a value, I don't quite know it yet, and we know our independent variable is t, but since the vertex is 20.5 as the y value, we know this is going to be plus 20.5, and I know that the vertex has a x coordinate of 2, and now we can use the process from previous module and just find the a value, because we need to find the zeros. In order to do that, we'll need to know what the a value is. And remember, to find the a value, we can use any other point on our table. So I'll use this one, the first point in the table, because if it's got a 0 in it, it might make my life a little bit easier. So this is 0.5 is the height. That height occurs at a time of 0. So if I find a, right here I'll get 0 minus 2 squared is 4. And if I move 20.5 to the left-hand side, I have negative 20 is equal to 4a. And then one step further, I'll get both sides divided by 4 gives me negative 5. Okay, so vertex form is h of t is equal to negative 5 t minus 2 squared plus 20.5. Now we've done this next step a few times, so now we're in vertex form. As for how do we turn this into factored form to find the zeros, we can do that in one of two ways. We can either rearrange this equation and solve for t, or we can do, as we've done in some previous examples, we can go ahead and expand this into standard form and then either try to factor it or use the quadratic formula. Now we've done an example of expanding and factoring, or expanding and using the quadratic formula. That's normally what we've done. Here I'm going to use the other option, and I'm going to just solve for t. Okay, so if I want to find the zeros, we know that, or in other words, if I want to find out here when the arrow will hit the ground, okay, I know that that means I have to find the time when the height is equal to 0. So I'm going to find t when h of t equals 0, I'm going to put a 0 in for h of t, and I'm going to solve for t. And this just means using opposite operations. So if I want to get t by itself, I'm going to have to do the opposite operations of bed mass. So start by moving addition and subtraction. So take the 20.5, move it to the left-hand side, it becomes negative 20.5. And then deal with any division and multiplication. I notice that I'm trying to get t by itself. In this case, the division multiplication means to divide both sides by negative 5. So this gives me positive 4.1. And I still have t minus 2 squared. And then the opposite operations for exponents, for squared in particular, means I need to take the square root of both sides. And I'm going to get both the positive and the negative square root of both sides here because I am going to get two answers, right? My zeros, if we can see from my sketch up above, I'm going to have 2 times when my height is equal to 0. So it's positive the square root of 4.1 and also negative the square root of 4.1. And now I just have t minus 2. And lastly, I can add 2 to both sides, so I get this. Now, if you would have expanded the vertex form equation and then used the quadratic formula, notice how similar this looks. This is the same thing you would have gotten. So this will give you the same answers. In this case, I just need to find out, I wasn't specified the level of accuracy, I'll just use 1 decimal place here. So I need the square root of 4.1, which is essentially 2.0. So I get 2 plus 2 and 2 minus 2. So that makes sense that we have one value of t, which is 0, because it looks like from our model, oops, the other one there is 4. It looks like from our model that we have this whole function crossing through at the origin, and then the other one is 4. So when I look back to what I was asked originally, I was asked to find when the arrow would hit the ground. And I now have identified 2 locations. I've got time is 0, and also over here, a little bit of my graph, I've got time is equal to 4. And so now I know that the arrow, I think it's an arrow, yes, the arrow hits the ground after 4 seconds. So just to make a note, one question that we've looked at before previously asked, how long was this thing in the air for? This is slightly different. When will the arrow hit the ground does not take into account when it left, or rather what time it was fired into the air at. Here it was fired into the air at 0 seconds, so essentially those two are the same thing. Because it left and we started recording right away, it not only hit the ground after 4 seconds, but it was in the air for 4 seconds, okay, because there was a total of 4 seconds that elapsed between those zeros. But it's not always the case, as we saw in a previous example. If this arrow would have left the ground a little later, it is possible that the arrow would have hit the ground at 4 seconds, but it was in the air for less than 4 seconds. Okay, but it so happens to be the case here that it's the same.